Hello, welcome to this review of Chapter 4. So, I've put together a lot of problems that should be pretty representative of essentially what will be the test for this chapter. So, we're just going to go through them and kind of go over the things that we've learned so far. So, this is, in the textbook, this is sections 4.1 to 4.6. So, we'll start off with this section here right at the beginning. This is from 4.5, I believe, where we graph sine and cosine. Remember, the main things we learned about in this section were amplitude, period, vertical shifts, and phase shifts, right? How to find those out and what that means for the graph. And in this case, I'm not going to have you guys focus on phase shifting at all because that tends to make the graphs a little complicated. So we'll just stick to amplitude, period, and vertical shift. So where do those show up? I'll do f of x over here. Well, the 2 is my amplitude, right? We called this A, and the amplitude is literally that number. The B value is the number inside next to x. And the B value is what tells us what the period is. So we actually have to do a slight calculation here. So the period, remember, is 2 pi divided by b, which in this case would be 2 pi divided by 1/2, right? That's going to become 4 pi, right? So it takes 4 pi units for this sine function to repeat itself. And this minus 1 out here, that's going to be my vertical shift, right? So if you think back to function transformations, that's going to move the graph down by 1 unit. So let's see what we got here. So I know a full period is 4 pi, right? So let me go ahead and put 4 pi over here. And also remember, when it comes to graphing these functions, we usually look at the outputs of the function for the 4 quarters of the period. So that would be at 2 pi, at pi, and at 3 pi over 4. Or sorry, 3 pi. 3 pi, right? We want to break the period up into quarters like this because usually we find the zeros of the function or the maximum or minimum values here when it comes to sine or cosine. So keep in mind, right, there's a vertical shift here, which if you remember, this essentially tells us a kind of, I call this an equilibrium line, but in the notes it was referred to as the axis, right? And so the amplitude is always the distance from the axis. So from the axis, this sine function goes up by at most 2 units, and then it goes below the axis by at most 2 units. So let's go ahead and scale this this coordinate system here. Let's call this -2, and then this -4. This is at 0, that's at 2, and that's at 4. And now let's just plug in some values, right? So we have, let's plug in 0. 2 sine of 1/2 times 0 minus 1. 1/2 times 0 is 0. Sine of 0 is equal to 0. So we effectively have 2 times 0 minus 1. Right? That's going to give me -1. So the output of this sine function at 0 is here. Oh, you know what? I made a slight mistake on the axis. For whatever reason, I put it at -2. Right? But our vertical shift is at -1. I think I placed the axis there thinking that would be -1, but then I labeled it with a -2. So yeah, that's where the axis is. My mistake. Let's plug in pi, right? So sine of 1/2 times pi minus 1. Right? All I'm doing is I'm replacing the x with pi. Well, sine of pi over 2 is exactly 1, right? So this turns into 2 times 1 minus 1. That's +1. So that's going to be somewhere up here. And let's do maybe one more point just to be absolutely certain about what's going on, but I think this should take us back down to the axis. So let's see, 1/2 times 2 pi. Okay, well those cancel, so that's just pi. Sine of pi is 0, so we have 2 times 0 minus 1. That's going to be -1 again. And so if you think about what happens next, right, at 3 pi, we should go down, down to, let's see, my amplitude is 2, so I should go down to -3 here. And then I should go back to the axis there, right? And so we have a curve like this. And kind of like that, right? So that's my sine function, right? That's f of x, right? This is the graph of f of x. So a couple things to keep in mind. Number one, on the test, you will have a whole coordinate plane already made for you. You won't need to scale it yourself like I did here. You won't need to worry about phase shifting, right? And they'll just be examples more or less like this, right? And so if you followed along with me so far, maybe try to do this g of x on your own, and I'll be posting solutions for these after I review this with the class. So try it out, see what you can do, right? But just notice the amplitude here, right, of 3. Right? We have a b value of 1, right, which would tell you the period is 2 pi over 1. So that's just 2 pi. And then that 3 over here, that's your vertical shift. But, right, so just identify those things, plug in some values to get 3 values on the graph there, and then just try to fill in the rest according to what you know about sine and cosine. Right? But I don't want to waste too much time on this section. This is a very small part of the test. Let's move on to a different one, having to do with angles, reference angles, and converting between degrees and radians. So for the following angles, find the reference angle and convert the angle from degrees to radians. So we're just going to try to find both of those at the same time for a given angle. Let's start off by just converting them, right? How do we convert an angle? Well, if we have degrees, right, you multiply by the conversion factor pi over 180 degrees. And the reason for that is so that the units of degrees cancel out. You have degrees on top, degrees on bottom. They cancel each other out. You want to leave this answer in terms of pi, right? Don't give me a decimal here. Don't try to calculate that numerator. Just leave it alone. And just simplify the fraction in front, right? So 320 over 180. Let's divide that by, let's see. Let's divide it by maybe 20, right? So that's going to be 1/6 on top. On the bottom, that's going to be 9, right? So I think that should be fully simplified, right? So this is the angle in radians. Let's do the same thing with this 135 degrees here. Okay, so times pi over 180 degrees. All right, that's going to be 135 pi over 180. Looks like they both have a common divisor of 45, right? So that's going to be dividing 135 by 45 is 3. 180 divided by 45 is 4. So this is really the angle 3 pi over 4. That's a unit circle angle. And then maybe I'll do one of these over here, right? So even if the angle is a fairly big one, which this one is, right, you still just use the same process. So now, but instead, right, since we're starting with radians, we've got to multiply by the conversion factor 180 degrees over pi, right? And the goal here, the reason why we do the reciprocal, so that these pi's cancel out with each other. So let's see. We have 18. I'm going to write it this way. 18 times 180 degrees over 4. I'm not going to multiply the numerator because I actually want to simplify this stuff Let me sort of focus in on the 180 over 4, right? And then I'll multiply by the 18 later. 180 over 4, that's going to be 45. Okay, and then we can go ahead and multiply this out here. So what is that going to be? Well, let's see. Well, let me put it this way. I don't have a calculator next to me, but I know 18 is 20 minus 2. 20 times 45 shouldn't be too bad. That's 900. And then 2 times 45 is 90. Yeah, so this should be 810 degrees. Right? That's a little math trick. I don't expect you to know that, but I was just a little lazy and didn't want to grab my calculator. I'll leave that last one, right, just open-ended. You'll see the solution for that later. Now let's go ahead and find the reference angle. Now that one, this is not too bad, right? But you got to be aware of which quadrant you're in the unit circle. So 320. I know that it's going to be somewhere around here, right? That this is going to be 320. How do I know that? Well, I know that this is my 270 line and that this is the 360 line. And it's got to be between those. And of course, it's a positive angle. We're going counterclockwise. So my reference should be this one, right? There's my theta prime. And so what is theta prime? Well, that's going to be the next biggest angle from the we want to find that sort of measured angle to the x-axis there, right? So we could simply just take 360 minus 320. That's going to give me 40 degrees. If you want to, you can try to convert that to radians, but we'll go ahead and just find the reference angles in terms of the type of angle we started with. So we started with the degrees. Let's get the reference angle in degrees. All right, let's do 135. 135 should be right around here. That's a unit circle value, right? We learned that in 4.2. And so the reference angle should be this angle, right? That's the shortest distance to the x-axis. Okay, what is that going to be? Well, that's going to be, right, this is the 180 line. So just take 180 minus 135. It's 45 degrees. Remember, reference angles are always positive. All right, now this one's going to be a little tricky, right? But we can still do it. And this is where knowing the angle in degrees might be a little bit easier to do, right? So I know that 2 full circles is going to be 720 degrees. And so from there, I can figure out the rest. But I know if I go around 1, 2, right, that's 720. Oh, whoops. 1, 2. So that's 720. 810 is 90 degrees bigger than that, right? So that's going to go all the way to this angle line. So that whole thing is 810 degrees. All right. What's the reference angle? Well, you can actually go to the left towards the x-axis or to the right because both directions are going to give you a reference angle of 90 degrees, right? This is my reference angle. Or alternatively, right, you could go the other way too. I'll put it in a different color. Doesn't really matter. You're going to get the same answer regardless, right? So the reference angle is going to be a right angle. In radians, that's going to be pi over 2, right? We want our reference angle to be the same type of angle as the one that we started with. And I'll go ahead and leave that fourth one for you to try out if you haven't already tried one yet. All right, let's go down a little bit more. We've also got this unit circle. We'll go ahead and fill in a bunch of these values. The most important part about this circle for sure is this first quadrant, right? So we definitely need to know these values. I'll go ahead and start with the degree lines, right? So this is 30 degrees. That's 45. That's 60. This is 90 degrees. And I should probably put down here, right, 0 degrees for this line. Those are the most important angles to know the radians for and the coordinates for, since those are going to tell you what sine, cosine, and tangent output, right, what the output for those functions are. Now let's do the radians. Radians, remember pi over 6 is with the 30. We've got pi over 4 with 45, pi over 3 with 60. And then pi over 2 with 90. And of course, 0 degrees, same thing as 0 radians, right, for that 0 degree line. And then remember, the coordinates follow a pretty consistent pattern, right? There's those square roots, right? And then you also usually have a 2 in the denominator. So like this one over here, for example, is radical 3 over 2, comma 1/2. Then we have radical 2 over 2, comma radical 2 over 2. And then 1/2, radical 3 over 2. Now these on the ends of the quadrants, right? This one is 1, comma 0 for the 0 degree line. And then we have 0, comma 1 for the 90 degree line. Now let me take a pause here and just show you just how important it is to know these, right? If we go down here, we can actually fill in all of those expressions, what they're equal to, just by knowing that first quadrant. That's it. Because remember, right, the x-coordinate is your cosine, the y-coordinate is your sine, right? And the theta is the angle on that angle line, right? So, for instance, sine of 30 degrees, go to your 30 degree angle line, right? Sine is going to be this one, 1/2. So I know sine of 30 degrees is equal to the number 1/2. Boom. Anywhere I see a sine of 30, I can swap it with 1/2. Sine of 45 degrees, that's going to be this one, right? And the sine is going to be radical 2 over 2. Right? So the answer is radical 2 over 2. Sine of 60, same thing, right? Go to 60 degree angle line. Sine is going to be this one. So it's radical 3 over 2. Sine of 0 degrees over here, right? That's going to be the 0. And sine of 90, right? That's going to be the 1. So 0 and 1. Let me do it in a different color here. So what about the cosines, right? Cosine of 30 degrees. Again, go to your 30 degree angle line. That's your cosine. Radical 3 over 2. Cosine of 45 degrees. Boom. Boom. Radical 2 over 2. Right, and so hopefully you get the picture by now, right? This one will be the 1/2, right? This one will be 1 and 0, right? So if I go back up, here's my 60 degree line, right? There's the 1/2. The 90 degree line, there's the 0. And the 0 degree line gives us the 1. So the outputs for sine and cosine come from the unit circle. Right, so that's why it's so important just to know at least that first quadrant. So let's go ahead and fill in some of the rest of these, right? We have, we saw this one before. Oh, hold on. Okay, so we're back. We have the 135 degree line. We have, let's see. That 135 degree line gives us this coordinate over here. In radians, this angle over here, that's your 2 pi over 3. And that's very similar to the pi over 3 coordinates, right? The only difference is we have negative 1/2 here, and then radical 3 over 2 here. Over here we have the 5 pi over 6 radians. And then on this 180-degree line, that's your pi radians, right? Coordinates here being negative 1, 0. So I don't want to fill out the whole thing. I'll leave some to you. Again, you'll see the solutions later. Let's move on to this next page over here. So solve for the missing sides and angles. I'll probably do one triangle with degrees, one triangle with radians right now. I'll actually need my calculator here to do this. What's crucial here is you got to make sure your calculator is in the right mode, right? But first, before you even touch your calculator, you got to set up the equation. So I'll go ahead and work on this one here. The way I usually approach these is just with SOHCAHTOA, right? So look at your angle. Across from that angle is my opposite, right? Then I got hypotenuse over here and adjacent over here. Right? And I just want to find all these missing sides and all of the missing angles. Let me find the sides first. So SOHCAHTOA. If I use the sine equation that comes from the that tells me that sine of 20 degrees equals 10 over h, right, the hypotenuse. Well, if I solve for h, that tells me that h equals 10 divided by sine of 20 degrees. Right? And I'm going to save all the calculator work for the end, right? So let me go ahead and also solve for the adjacent, right? You're going to want to use the cosine equation. That's telling you that cosine of 20 degrees equals a over the hypotenuse, which I guess I'll have to get that hypotenuse here. Or in fact, actually I can avoid that, right? By using the TOA equation. So let me redo this with TOA actually. It's better to use exact values whenever you can. The TOA tells me tangent of 20 degrees equals 10 over a. And if I solve for a, that tells me my adjacent side is 10 divided by tangent of 20 degrees. So now let's figure these things out, right? Let's see. Let me check my mode. You got to be in degree mode. Looks like I am. Let me do 10 divided by sine of 20. That gives me an answer of about 29.24. Right, so that's this hypotenuse, 29.24. 10 divided by tangent of 20. That gives me an answer of 27.47. 27.47. All right. And then finally, to get that last angle, right, we just got to take 90 minus 20. So that tells me this angle is 70. Another good way to check to make sure your sides are correct is to take your two legs of the triangle, compute the Pythagorean theorem, and you should get an answer very close to your hypotenuse, right? So if I were to take 27.47 squared plus 10 squared, it should give me roughly 29.24 squared. So let's see what we get. Squared plus 10 squared. So that gives me an answer of 854.6, right? If I take the square root of that, I get an answer of 29.23, which is very, very close to the hypotenuse over there. So I probably didn't make any mistakes here, is the point. I was just checking my work to make sure it makes sense. All right, let me go ahead and do maybe a radian version, right? So now I'll move on to this triangle. Make sure your calculator's in radian mode. So I'll switch the mode here. Click on mode, radians, good. If you're not in the right mode, you will get the wrong answer. Now, actually, you know what? Instead of doing the skinnier one, let's do something a little different. Let's do this one at the bottom right here, just to change things up, right? So this is my angle. Across from that is my opposite. The 12 is my hypotenuse, which leads this side over here as my adjacent. All right. Now let's set up some equations. Let's use our SOHCAHTOA. Right? We'll go ahead and start with the sine equation. That tells me sine of 4 pi over 9 equals my opposite over my hypotenuse. And if I solve, that tells me the opposite side equals 12 times sine of 4 pi over 9. I'll go ahead and calculate that. 12 times sine of 4 times pi over 9 gives me about 11.82, which makes sense. 4 pi over 9 is a fairly big angle, so we should get an answer that's very, very close in length to the hypotenuse. Now let's go ahead and use the k of SOHCAHTOA. That gives me this cosine equation, right, of this angle is equal to the adjacent over the hypotenuse, which is 12. Right, so very similar here, right? This tells me that the adjacent side equals 12 times cosine of 4 pi over 9. All right, let's calculate that out. 12 times cosine of 4 times pi over 9. That's giving me a length of 2.08. Right? So this length equals 2.08. This length is approximately 11.82. And how do I find this angle over here, right? So for that angle, I would take a right angle in radians, which is pi over 2, and then subtract away the 4 pi over 9. And so we'll have to combine these fractions here, right? So this is the same thing as 9 pi over 18 minus 8 pi over 18. This gives me an answer of pi over 18, right? So that is a very, very tiny angle. Very, very tiny. And so, yeah, the side across from that tiny angle should be pretty small, which is what we got. Again, you could check to make sure these sides follow the Pythagorean theorem, that you at least get something very close to the hypotenuse squared. But let me go ahead and move on. I'll leave the other two for you. Again, look for those solutions. And I'll tackle these word problems here. So this is a very standard trig problem. You'll see this phrase a lot about angles of depression or angles of elevation. This is the most practical aspect of trigonometry, how you can find unknown distances using all these angles in sine and cosine. So let's see. We have an angle of depression to the police car of 30 degrees, right? Now remember what that means, angle of depression. It means if you're looking straight forward, it's how much you have to rotate your head down to look at something, right? So if I have a little horizontal line that's parallel with the ground, right, that's looking straight forward, to look down at the police car, something like this, that is my angle of 30 degrees. Right? Okay? And let's see. I have an angle of depression to the street racer of 20 degrees. All right, so this red angle is 20 degrees. And there's actually something missing here that I should have included. I need to know, in order to solve anything here, I actually do need to know the height of the mountain, which I think I intended to put in. Looks like I forgot. Let's say that this mountain is, let's not make it too high. Maybe, let's make it about 3,000 feet. All right. Say the height is 3,000, which also, keep in mind, means that this length here is also 3,000, and that this length is also 3,000. And there are my right triangles, right? You always want to find a right triangle or maybe two right triangles if you're ever doing a word problem and using trigonometry. So now, here's the question. How far apart are the cars? And we have to sort of break this problem up into two steps. The first step is, okay, we know where these right triangles are. Let's go ahead and find some side lengths on these right triangles, because we know at least part of them. And let's find the side lengths that have to do, or, we can use to find D, right, which would be probably this leg of the blue triangle. We can call that, let's call it x1. Right. And then let's also find the other leg, which is much, much longer. Let's call that x2. And if we can find those two things, then we know that this distance here is just going to be x2 minus x1, right? Which is what D is. That's the distance between the cars. So we first need to find those two, right? Let's just set up the basic SOHCAHTOA stuff. So I'll do this blue triangle first. Here's my angle. Go across. This is my opposite side, right? Here's my hypotenuse. So the x1 is my adjacent side, right? And I want x1, and I know what my opposite is. So as far as SOHCAHTOA is concerned, there's only one possible part of that makes sense to use, and that's going to be the TOA. I want an equation that uses my opposite side and my adjacent, right? So this is the only one that makes sense to use. So that tells me tangent of 30 degrees equals 3,000 over x1. And if I solve for x1, that tells me x1 is going to be equal to 3,000 divided by tangent of 30 degrees. And I can get an answer here, right? Let me hold off on the calculator. Let's go ahead and solve for the x2 while we're at it. So for x2, right, let's focus on the red triangle. Across from my angle, this is my opposite side. Here's my hypotenuse, and that means my x2, that length right there is my adjacent side. So I want to find an equation that uses my opposite and my adjacent. Well, that's going to be TOA again. Right, so that tells me that tangent of 20 degrees is going to be equal to 3,000 over x2. And if I solve for x2, that tells me x2 is going to be 3,000 divided by tangent of 20 degrees. Right? So they're actually very similar calculations. So let's put this in. Again, make sure you're in the right mode. We're using degrees in our angles here. Go to degree mode. So you're going to have to change it if you were following from the last problem. And let's put it in. So 3,000 divided by tangent of 30 degrees. Okay. So I'm getting an answer of, it looks like 5,196.15 feet. I did it in the wrong color. That's okay. And quick tip, right? If you have two expressions that are very, very similar and you're using a TI, press second and then the enter button. and it has entry in yellow right above that. So it's going to take your last entry, copy it all for you, and then you can go back and change that 3 0 into a 20 0. That way you don't have to type it all out from scratch. Right. Press enter, and I should get a bigger distance this time, which I do. I get 8,242.43 feet. Right, you always want to make sure the numbers you're getting at least somewhat fit the picture that you're looking at. Right, I'm supposed to get two numbers that are bigger than 3,000 for sure. And the second distance should be bigger than the first. Right, so when I find the final answer, right, that's going to be D. That's going to be x2 minus x1. Right, I just take those two numbers and I subtract them. Right, so 8242.43 minus 5196.15. So the distance between the police car and the street racer is 3,046.28 feet. Right, so hopefully all those steps are pretty clear. Right, so whenever you have these pictures, right, just try to find the right triangles, label your sides using SOHCAHTOA, and give names to stuff you don't know, right? You didn't have to call these X1 or X2 or D. You can actually give them any names that you want. By the end, if you set up the equations right, you're still going to get the same thing. So just make sure that you give a name to any unknown lengths so that you can put those in your equations and then you can solve for them. And make sure you're doing it in a way that makes sense, right? So like in this problem, it didn't really matter what the hypotenuses were. We didn't really care about those, right? They didn't help us solve for what we're trying to find, right? We wanted the leg of the triangles on the top here, right? Right, we wanted this leg and also this longer leg at the top. So look for stuff that's actually going to help you solve the problem is the main point. All right, and then let me go down here. So we have a sort of real-world application. This is from 4.6. We talked about the damping factor, right? So our damping factor is essentially this part right here. This is our damping factor. And remember what that does is it basically incorporates friction into our model. So we can imagine if there's friction in the system over here, that the oscillations, the back and forth movement of the mass are going to get smaller and smaller, and eventually it's going to stop moving because the energy is completely dissipated. So these are just some straightforward questions where you could essentially solve these without knowing any of that anyway, because you have the function equation, right? So t is time, d of t represents the position of the mass, right? It's the position away from this wall over here, right? So let's just go ahead and use it as we were given it. So the first question, what is the initial position? That means initial position, that's when t equals 0, right? So let's just plug in 0, right, into this function. It's going to be 2e to the negative 0 times cosine of 0 plus 5. Right. What is that going to be equal to? Well, this is 1. This is 1 as well. So we really just have 2 times 1 times 1 plus 5. That gives me 7, right? 7, let's see, do we have any units here? We do not. Let's just assume this is in meters. Usually in physics problems, you're using meters per second anyway. So let's just assume it's meters, right? What is the position after 2 pi seconds, right? Do the same thing. Plug in 2 pi into the function. So that's going to be 2 times e to the negative 2 pi times cosine of 2 pi plus 5. And this is after some time, so some friction has already occurred. Right? So we should expect kind of a smaller number here. Right? So cosine of 2 pi gives us 1. Now that e to the negative 2 pi is going to be a fairly small number, right? So basically from here on out, I'm going to go ahead and just put this into my calculator. But I know that this is what I have right now. And let's see what we get. 2 times e to the negative 2 pi, right? And then plus 5. And that gives me 5.004 meters, right? And think about this, right? After 2 pi seconds, you've done a full cycle for the cosine function. So it should be reaching its maximum value again at 2 pi. But notice how from 7, it should have reached 7 again, right? But the friction has reduced the amplitude down to 5. Right? And it should keep doing that, right? And so that's going to help us figure out, what will the position be after a really long time? Well, just think about what friction does, right? It's just going to slow this oscillation down until it's not really wobbling anymore. So there's a couple ways you can approach this. One way is you could take this function and just plug in a very, very, very big number, right? And you could find an approximate answer there, right? So you could literally try to calculate, okay, what is 2e to the negative 10,000, right, times cosine of 10,000, and then plus 5. That's fine, right? That should give you a pretty good answer, or at least tell you what it's approaching. So let's see what we get here. 1, 2, 3 times cosine of 10,000 plus 5. It looks like we have an overflow here. We might have to use a smaller number. Let's go ahead and make it 1,000. See if that works. Oh, still an overflow. Okay. Let's try 100. 100 might be good enough. Okay. Interesting. So I'm getting an answer of negative 9.3357 e to the 42. Oh, you know what? That is incorrect because I forgot to do e to the negative 100. I put e to the 100, which is why I was getting such a big number. So let's try that out. Yeah, we basically, the calculator doesn't even bother with decimal places. It just gives me the answer 5. Right? So basically, the wobbling has essentially stopped, right? And the mass is just sitting at 5 meters, right? And so that would be what we call the axis of this function here. So anyway, that should be the last problem. Hopefully this has been helpful to you. Again, look for those solutions for the problems that I didn't try. And thank you for watching.